Okay, perhaps let us begin.
Okay, I'll try to share my screen.
Okay, so our next speaker is Professor Ruth Durrer from Geneva, and she's going to talk about testing generativity with cosmological large-scale structure. Maybe I'll send you a reminder when 5 minutes are left.
That's very good. Do you see my screen?
Yes, I do, but perhaps this is not the full screen.
Oh, okay, so you don't. So maybe I stop and I share again. Do you see it?
Yes, yes.
Okay, very good. Yeah. Okay. The topic of my talk is testing general relativity with cosmological observations of large-scale structure. I will first give a motivation and introduction to this, and then I will explain you what actually is measured when we measure very large galaxy surveys. I will talk about the power spectrum of galaxy surveys, the angular power spectrum, the correlation function, the transverse and the radial power spectrum, and then I will specify on ways to test general relativity, especially by measuring the lensing potential, by the so-called EG statistics, which I will explain what this is, and by measuring the growth rate of perturbations. As you all know, Einstein's theory of gravity has been tested in many, many ways, and it so far passed all the tests with flying colors. We have in the solar system light deflection, perihelion advance of Mercury, and many other. Actually, perihelion advance we have now measured in many other binary systems where it is much larger than in Mercury, then Shapiro time delay, etc., other classical tests. And since nearly 10 years now, we also have seen gravitational waves. So why might we want to test general relativity with cosmological observations? There are two reasons. One of them is that all these tests are on scales of the solar system or so and not much larger, while cosmology is on much larger scales. But there is also another reason which I find kind of interesting to note is that all these tests are essentially testing the vacuum solution of Einstein's equations. While how can we test? Can we test these equations also in the presence of matter? And there, of course, cosmology comes to mind. Cosmology, here we have on the right-hand side, as you see, matter terms. So this is a non-trivial solution which is non-vacuum. Now the question is, have we tested this solution with cosmological observations? Let us reflect on this a little bit. For example, let's think of supernova observations or something like that. What we measure there is the flux from a supernova of which, or a supernova type 1a, of which we kind of, very crudely speaking, know the intrinsic luminosity, and therefore we can infer the distance to the supernova. And this distance, the luminosity distance, gives us information about the expansion rate h if we know it to many different supernovae. H is just a dot over a. We get this integral of h, a function of the integral of h, while this function depends on the curvature. If curvature vanishes, this function is simply r. So we have measured this distance to many, many supernova type 1a, and that is kind of the result from these measurements. These measurements have led us to a universe which contains a lot of dark energy, namely 70% of the energy budget of this universe is dark energy, and about 30% is matter, and the curvature is compatible with zero. Here, I like this somewhat old plot. Here on the y-axis, you see a quantity which is the observed minus the intrinsic magnitude, which is proportional to the log of the distance. And here what we plot actually a delta of this, which is the log proportional to the log of the distance divided by the distance in a Milne universe. So in a universe where you have only negative curvature, but no matter, that would be here the zero line. So you have neither accelerated expansion nor decelerated expansion. The scale factor is linear in time. And you see the observed universe is only compatible with something which has acceleration first and deceleration at higher redshifts. But is this a test of general relativity? Actually, not at all. No, we have assumed the Friedmann equation. So we have assumed that general relativity holds and inferred that therefore matter must consist of mainly some matter with very negative pressure, which accelerates the expansion of the universe, and some ordinary matter, which, however, also is much, much more than the baryonic matter in the universe. The problem here is that given an arbitrary expansion history, nearly, one can always find matter which generates this expansion history. So for example, if we only request that the Hubble parameter was larger in the past than what it is today, then we always find a scalar field which gives us an arbitrary expansion history which just satisfies whatever we want. So in order to test general relativity, it is not sufficient to look at the background universe. We must consider clustering. We must consider the small fluctuations on top of the Friedmann universe which we observe. We have done so with very high precision in the CMB, in the cosmic microwave background. There we have seen fluctuations on some three and more orders of magnitude in scale of the temperature of the CMB. These fluctuations are very small. This is, here you see it in microkelvin squared, so they are of order 10 to minus 5, a few 10 to minus 5. And what we see here are the so-called acoustic oscillations. We see that the universe, when the universe was still in, photons were still in thermal equilibrium with electrons and protons, the photon pressure counteracted the collapse of gravity and led to oscillations, really acoustic oscillations, determined by the sound speed, which is roughly 1 over square root 3 of the photons. And so we can calculate these acoustic oscillations and the signature which they should have left on the CMB. And what we get is these blue curves, which are in perfect agreement with the data. So we kind of really understand the matter content or the dominant matter content of the universe before recombination in the early universe. So it was to a very good approximation. Radiation dominated at early times. We also need to explain this curve a component of free streaming relativistic particles, which exactly corresponds to 3 species of neutrinos with very low masses. So we also see the neutrinos in these fluctuations. But they test very precisely the universe before recombination, and there is a little bit of things that happen after recombination, namely a lensing of CMB photons, deflection due to foreground structure, but it's an integrated effect and it's not very precise. To precisely test what happens after recombination, it's probably more suitable to look into the distribution of matter in the universe at later times. Here you see a distribution of pardon, of the galaxy distribution as seen by DESI. These are different types of galaxies which they will observe, which they are observing close by and at intermediate redshifts and at very large redshifts, because there are different things which you see. And close by, they'll have the bright galaxy catalog, and then they have the some line galaxies, and then they have the luminous red galaxies, emission line galaxies in between, and then luminous red galaxies, which they observe. And so if we can understand these fluctuations which you see here by naked eye, then maybe they can help us to test general relativity. For example, these baryon acoustic oscillations, which we have seen in the CMB, are actually also seen in the galaxy distribution. Here you see a picture from the DES dark energy survey, which is not the same as the one I've shown you just before, but it's a slightly older, where the redshifts of the galaxies are not very, very well constrained. They are so-called photometric redshifts. Here you see this is data from redshifts between 0.6 and 1.2. And it's slightly, this is the baryon acoustic peak in the correlation function, which slightly differs from the one seen by the Planck data. If one assumes the Planck cosmological parameters, one gets a slightly different curve. But this is not yet a really significant deviation. If we want to talk about I would like to hide this thing here. Yeah, but anyway, I don't manage. If we want to talk about galaxy surveys, we have to think about what we are actually really measuring. If we look into the sky, of course, all we see is our past light cone. And this past light cone is perturbed by the perturbation of the geometry. More precisely, so this means that density fluctuations, which are further away from us, we see them further in the past. We can never observe a constant time hypersurface. We actually see two spatial and one light-like dimension, or rather precisely what we measure are two angles and the redshift, right, when we measure a galaxy survey. And the measured redshift is also perturbed by peculiar velocities and by the gravitational potential. And furthermore, not only the number of galaxies, but also their volume is distorted. And if we consider density fluctuation, we count galaxies and divide by the volume. The angles we are looking into are not the ones into which the photons have been emitted, but they have been deflected by the foreground structure. For small galaxy catalogs, these effects are actually not very important, apart from the velocities which are being taken into account systematically. But when we go out to redshifts of order unity, they really do become relevant, especially for present surveys and near future plans. In a Friedmann universe, the co-moving radial distance is just the integral, the redshift integral of the inverse Hubble parameter, which of course depends on the cosmological model. Here I have written what it is in a lambda CDM model, maybe allowing for curvature. if you have some other dark energy, some evolving dark energy, this integral, you have to replace what I called omega lambda by this evolving dark energy. But what is important here, it depends on the cosmological model. And correspondingly, the angular diameter distance or the luminosity distance also depends on the cosmological model. As long as the redshift is much smaller than 1, all these integrals more or less just give you c over h naught. That's the first order in redshift term for all these distances. But once you go to redshifts of order unity, this is no longer a good approximation, and the distances depend strongly on the matter content of the universe. So whenever we convert redshifts and angles into length scales, we make assumptions about the underlying cosmology. And for radial distances and transversal distances, actually, the underlying cosmology enters in different ways. Here, just as an example, if you consider the correlation function of galaxies here in lambda CDM at redshift 0.7, and that's what you observe as a function of the angular separation of the galaxies. And you convert this into a correlation function as a function of the distance between the galaxies. Depending on what your assumptions are about the matter content, you get something else. And the same is, of course, true for the power spectrum in Fourier space, which is nothing else than the Fourier transform of this correlation function. So whenever you see a power spectrum and observers tell you that they have measured this is not quite true. There is always an assumption about the underlying cosmology going into a power spectrum in Fourier space. If we consider very large galaxy surveys and we consider the fluctuation in the matter distribution and the geometry to first order in perturbation theory, we get an expression which is rather involved. What we truly measure is, as I said, the direction and the redshift, and maybe other information about what type of galaxy we are looking at. And what we then can, the fluctuation of the count is then the number of galaxies we measure in a given small solid angle and in a given small redshift bin, minus the mean of galaxies in this redshift bin. This is the fluctuation of the number count, which we can truly measure and which we can also compute. And then we can compute its correlation function, which under the assumption of isotropy is simply a function of the angle between the two directions and, of course, on the two redshifts. This quantity is directly measurable. And so we have computed it in linear perturbation theory. We have also computations at second order in perturbation theory, but they are very long and the results cover several pages, so I'm not going to write it down. But at first order, it's still reasonably understandable what we see. This first term is just the density fluctuation, which typically is biased in galaxies, so that has to be multiplied by a bias factor, which depends on the type of galaxy you look at. Then there is this redshift space distortion, which comes from the fact that the radial volume is distorted by velocities. And then there is a second term to this as well. And then there is a lensing term. This integral here is nothing else than the convergence. This is the angular Laplacian of the sum of the two Bodin potentials, the sum of the two scalar perturbations of the metric. And this term can have both signs. It has actually two effects. On the one hand, due to lensing, you converge, you have convergence due to foreground structures, which means that you assign a larger angular angle to the distance between two galaxies, so a lower density, this is this factor -2. On the other hand, this convergence also makes that if you are looking at if your telescope has some fixed sensitivity, has a flux limit. If flux is fainter than that, you will not see the corresponding galaxies. You have some galaxies where the flux is enhanced sufficiently that they actually make it, due to this foreground lensing, into your survey. And if there wouldn't be any amplification, they wouldn't make it. This is this factor 5S. The factor 5 here comes from the strange definition of this S. So this is a quantity which depends on your telescope, on your survey. And if your survey would see all the galaxies there are, then this would simply be 0. But that is usually not the case. The other terms here are integrated Sachs-Wolf effect, Shapiro time delay, and the gravitational potential, other Sachs-Wolf terms which appear here. And these terms are rather small. But if you here, just as an example, that this redshift space distortion has been measured well. Here you see results from the BOSS survey in 2 redshift bins. You see the squashing which comes from linear perturbation theory, namely that if you here in the middle is supposed to be some galaxy cluster, so the foreground galaxies seem further away from us because they fall into this cluster, and their redshift is larger than it would be without it, while the background galaxies, they also fall into this cluster, so their redshift is a bit less than what it would be, and so we put them less far away than they actually are from us. So this leads to this squashing here. And these so-called figures of God in the middle are due to the fact that around the cluster there is virialization and galaxies move rather fast in all directions. And so you have larger velocity, so a larger spread of redshifts than you would have if there wouldn't be a cluster. So as I said, this number count fluctuation is a function on the sphere, so we can expand it in spherical harmonics as we did with the CMB. And these coefficients are uncorrelated for different L's and M's due to statistical isotropy. So we can define an angular power spectrum like for the CMB, but in this case, this angular power spectrum depends on 2 redshifts, namely the redshift of the number counts in the foreground and another redshift of number counts in the background, which you're correlating. Of course, the correlation is largest if you choose C equal to C prime. And the correlation function is then simply given by the sum over these CLs times Legendre polynomials, as for the CMB. The contribution to this transverse power spectrum at now C equals C prime, very small redshift, is mainly dominated by the density term, which we always took into account. And so at very small redshift, these corrections are really irrelevant. There is a bit coming from the velocities, and that velocity density correlation, that term would be larger if we would choose the redshift bin width smaller, that like 10 to minus 3 or so, then this can actually get a factor of 10 or more, even larger. And that's the 2 quantities which have been taken into account so far. However, if we go to high redshift, here again an extreme case, redshift 3 and a wide redshift bin, then suddenly the lensing term, this kappa, this convergence kappa, becomes very important, can actually dominate over the density fluctuation. And if we look at the radial correlation function, namely the C as L's for a fixed L as a function of C prime for a fixed C, we find that at low redshifts, it's again the standard terms. Here the blue is density plus redshift space distortions added together. The cyan is a Doppler term and the magenta is a lensing term. They are again several orders of magnitude smaller than the standard term. However, if we go to higher redshift, they grow up, and at redshift 3 or already at redshift 1, if we go to significant redshift distances, they become relevant. If the redshift difference becomes important. Actually, what we have found is if you correlate density fluctuations or number count fluctuations rather at different redshifts, you can actually isolate the lensing term. If we compare the number count correlation at different redshifts, we find that they are more or less given by the lensing of the convergence potential of the background times the density of the foreground. This lensing kappa, as you have seen, was an integral along the line of sight, and that picks up, of course, the densities in the foreground. For example, if you correlate the first bin of Euclid with itself, you find that this lensing, which is here shown as the magenta dotted line, local lensing correlation, this second term, is completely negligible. But if you correlate bin 1 with bin 4, it is already quite relevant that you include it in order to get the black total curve. If you only take the standard terms, you would expect something different than what you really see. And if you then go to correlate bin 1 with bin 10, you only see the lensing term. You can really isolate the lensing in this way. But all of this is, of course, really telescope or survey dependent. Here you see bin 1 correlated with bin 4 for so-called magnification bias S of Z taken for Euclid, while here it's taken for SKA. For SKA, you see already a very different result already. Correlating bin 1 with bin 4 with SKA will be dominated by the lensing term because of the different values of this magnification bias. Let me skip to this plot immediately. Here we made a little study, how well can one actually determine this lensing part to the contribution to the number count by just multiplying the lensing part with a constant beta, and the true value of this constant beta in GR would be 1. How well can we constrain this parameter? Here you see just a couple other parameters. In the previous plot you saw all of them, but it's a bit too many. But what one sees, it's going to be on the few percent level, like also other parameters like neutrino mass, Hubble parameter, amplitude of the perturbation, or so. But what is different is here the red lines are the results for a 5-bin configuration, while the black lines are results for a 10-bin configuration. And splitting the data into 10 bins, we see that neutrino mass, Hubble parameter, and amplitude are much better constrained, while splitting them only in 5 bins is a less good solution. However, if we compare the case where we only take auto-bin correlations, that's the dashed lines, or where we take also all the cross correlations into account, in the 10-bin configuration, neutrino mass, Hubble parameter, or amplitude of fluctuations are not very sensitive to it. However, the variable beta, which determines the lensing part, is mostly sensitive to taking into account cross correlations. Whether we have 5 or 10 bins is not so important, but it's very important to include the cross correlations to measure it. Here we started with a MCMC code. What happens if one neglects this lensing term, which is actually has been done so far in all the analysis in the past? They have always neglect this lensing convergence in the number counts. And if we would do that with Euclid, which we don't plan to do, but what would happen, even if we take only autocorrelations into account, that's the gray results. If we only take autocorrelations and neglect lensing, the blue results, if we take auto and cross correlations, but we neglect lensing, and the red result is the correct analysis. The vertical lines are the input parameters for our simulations. You see, for example, one thing which is interesting, the bias factor, bias of the galaxy population is completely degenerate in this photometric survey if we have, or very degenerate if we have no lensing term. However, the lensing term fixes it. What is even more dangerous, if we assume there is no lensing in the data, we will assume that neutrinos are massive because the lensing leads to a washout of small-scale fluctuations, a little bit like massive neutrinos. So we will get a completely wrong neutrino mass. Here, the input neutrino mass was the minimal one of 0.06 electron volt. We would infer, even only taking autocorrelations into account, that the neutrino mass is like larger than 0.3 electron volts, etc. You see also the amplitude is very badly constrained if we don't take into account lensing, whereas with lensing we can really measure it because it's very degenerate with the bias. If we assume that the only thing we see are density and redshift space distortion, and the redshift space distortions are not well determined because this is a photometric survey, then we have this degeneracy. Here we calculated the signal to noise from the lensing potential. How well can we actually measure this lensing potential in galaxy surveys? And we found that the cumulative signal to noise for a kind of Euclid-like tomographic map is of order 30, 35, so nearly 40. So we can measure it very, very well. We will be able to measure this lensing potential, which will give us the gravitational potential, and which we can then relate to the matter fluctuations. Another test of general relativity is the so-called EG statistics. Photon propagation, which governs weak lensing, is sensitive only to the sum of the two gravitational potentials. This sum is actually the potential of the while part of the curvature, and photons only motion of photons is governed by the while part of the curvature and not by the Ricci part, while massive non-relativistic particles are accelerated by psi, which is the standard Newtonian gravitational potential, actually. Now, non-relativistic density fluctuation generate phi via the Poisson equation, and in standard GR, phi and psi are equal for ordinary matter. And so comparing galaxy surveys, galaxy number counts, and weak lensing surveys, one can actually measure the ratio between these two quantities, which will then be in standard lambda CDM, or if the only clustering component is ordinary matter, this function here is independent. This quantity here is independent of scale and is more or less given by the matter density to the power 0.55. One can also convert it into angular scales, where it is this quantity. However, we must be careful if we have galaxy surveys, we don't measure really delta. We actually measure the galaxies which we see, and as we have seen before, they are affected by convergence especially. Redshift space distortions are not so important if we are using photometric surveys, which are usually used for this type of statistics. But the galaxy surveys also contains the kappa delta and kappa kappa. So this has to be taken into account and corrected for. In principle, this can be corrected for because we can measure all these quantities also independently. And if we do not correct for it in a desk-like survey, we found that the change in the EG, if we do not correct for this, is on the order of a few percent. And since the precision of the EG test is of order 10 to 20%, this is not very relevant. But for a Euclid-like survey, these corrections will be on the order of 10 to 30, 40%. And so correcting for them is vital to get good results. So we will have to correct for them. Another test of general relativity is to measure the growth rate of the perturbation, which is very sensitive to the theory of gravity. Actually, only a cosmological constant will not cluster at all on any scale. So only for a cosmological constant or curvature do we have a growth which is totally scale independent and which we know very well. So it will be important to measure this growth rate. To measure this growth rate, however, we want to measure velocities via redshift space distortions, which means we want to have very good redshift resolution. We want a spectroscopic survey where the redshift is very well measured. The lensing convergence is actually not very relevant for the standard cosmological parameter estimation with spectroscopic survey. It changes the standard parameters by about a third of one standard deviation. So it's still something which you want to avoid, but it's not very relevant. However, if you look at the growth rate, this is what you see. Neglecting lensing, that's what you find for the growth rate, for example, in lambda CDM, which we looked at here in this paper. And including lensing, that's what you actually measure for the growth rate. So neglecting lensing, and you consider part of what actually is the lensing signal as your growth rate. And if we compare that with the error bars which we have, this is for SKA2, so it's quite futuristic, where we hope to measure the growth rate with a few percent accuracy. And here we see that if we neglect lensing, this will actually give us errors of the order of 2, even 2.5 sigma at the highest redshifts. At the highest redshifts, of course, this error is worse because the lensing signal is largest at highest redshift. It's an integration along the line of sight. The higher you go in redshift, the larger this lensing signal becomes. So clearly, if we If we would now see this orange line with the precision of SK2, we would say, oh, we have seen deviations from general relativity, where actually just we haven't done the analysis as we should by including lensing convergence in the galaxy number count. So that's a point which I want to stress, which is really important and which will, of course, happen in the future. So I already arrive at my conclusion. In the past, large-scale structure data mainly determined P of k or correlation function as a function of distance, or also the bispectrum of 3Ks, etc. But as I told you, these quantities require a fiducial input cosmology. Whenever we convert redshifts and angles into length scales and then into Ks, which are inverse length scales, and this complicates the determination, especially of error bars. It's also complicated to correctly include lensing because lensing is determined only on our background light cone. And to do a Fourier transform, we must know data on a constant time hypersurface, right? On which we want to do this Fourier transform, which we cannot really do. But of course, this is done in a way with the data which one can do also with the calculation, but it's rather complicated. It's explained how this is done in this paper. In future surveys, it might actually be an advantage to express the correlation function and power spectra in quantities which we directly measure, namely angles and redshifts, or the harmonic transform in multipoles and redshifts, and correspondingly with the bispectrum. These quantities will be more noisy as they depend on more variables, but they also contain more information. These spectra, as we have seen, are not only sensitive to the distribution of matter, to the density, but also to the velocity via the redshift space distortions and the Doppler effect, and to the perturbations of space-time, especially via the lensing convergence. We therefore can, in principle, determine both the components of the energy momentum tensor and the geometry, which allows us to test Einstein's equation. Especially the CLs of kappa times galaxy and galaxy-galaxy, so number counts, if one corrects them suitably, they are allowed to rather model independent tests of general relativity via the EG statistics. This can also be measured with intensity mapping. I didn't talk about that here, but that would be another subject. Also, the growth rate can be measured, and it's important to include lensing in order not to make mistakes there. For this, one needs spectroscopic survey, while the EG statistics can be measured with photometric surveys. And it also tests GR. And as I did the spectra, which we will be able to measure, the galaxy-galaxy, the kappa spectra, but also the shear spectra, which we also can measure. They depend sensitively and in several different ways on the theory of gravity, on the growth factor, on the relation between the two Bardeen potentials, and on the matter and baryon densities and velocity in the universe. So their measurements will provide a route not only to estimate cosmological parameters, but which I think will be more interesting in the future, to test general relativity on cosmological scales and in the presence of matter. Thank you.
Okay,